What exactly is sampling? We all have seen sampling before in our daily life. Like that time we went to the mall and encountered different samples of different foods, or the time we went to the farmer's market, or the time when our mothers gave us a sample of Brussels sprouts or any other food. But what we want to talk about is the concept of sampling in statistics. If you remember, we defined sampling or a sample as a subgroup or a subset of the population that is randomly selected. But we want to go deeper to define what sampling is. Why is sampling necessary? To answer this question, let's consider a hypothetical scenario. Suppose you are in charge of a strategic planning for your company, and your boss, the president, would like to understand customer profitability of the company better. But he needs an answer within an hour. On the other hand, there are a huge number of customers and purchase transactions for the company, which is not possible just to go through all of them in 1 hour. Then what can you do, or what should you do? So sampling here is a necessity because there is no other possible solution here. So this is an example of time constraint or practicality of the situation. There are other scenarios or reasons that make sampling necessary. So we go with the time constraint, which is we are constrained by time and it's just not possible to do the task within the given time. The next reason or scenario is practicality of situation. For example, suppose a biologist who wants to study a specific insect, but he cannot possibly have access to all the population of that specific insect. It's just not possible. He or she cannot even find them, right? So this is not just practical. So what he needs to do is just to go with a sample. The next scenario or reason is cost. And this is a big one, especially for businesses, which just doesn't make it justify to study the whole population because it's too expensive and the company cannot afford it, or can afford it, but they want to save cost. So they're going to go with sample, which is more affordable. Another reason is, for example, the test to destruction. Consider a company, a car manufacturing company, who has to test the safety of their cars. They can't just do this testing, which is destructive to every car, because it's going to destroy all of the cars. So what they're going to do instead, they're going to take a sample of their car that they have manufactured and test that car as a sample of all cars. Studying a population through sampling. Until now, we have assumed that we know all the quantities we need to solve a problem. For example, we know the mean, the standard deviation, or the distribution of the population. But in reality, we do not know these parameters or information, and we have to estimate them using a sample. So in reality, we do not know the average of the population, mu, or the standard deviation sigma of the population, or even the size of the population, or the distribution of the population. So what we do is we take a random sample, which is a subset or a subgroup of members of the population selected randomly, and then in that sample, we compute the average of the sample, or x bar. We know the size of the sample, and we compute the standard deviation of the sample, which is s. And based on this, we can make an estimation about the population, or inference, draw an inferential conclusion about the population. So here, x bar is an estimation of mu, and s is an estimation of sigma, a point estimation. However, there is a problem here, and that problem is each time that we take another random sample, these values, these estimation might actually change. This is what is called as sampling error. What are the characteristics of a fair sample, or what should be the process of selecting a sample so we would have a fair representation of the population? A sample should be both random and representative. A sample is considered random if every item in the population is equally likely to be selected in the sample, or each item should have the same chance to be selected. A sample is representative if it accurately reflects the members of the entire population. The size of a sample is a factor of its representativeness. For example, suppose we want to study the age of a population, for example, a city. We have all sorts of diversity in the city population, but a random sample of this population cannot be, for example, picking a high school students, because that's not random, nor it is representative, because the age of, or the average age of students in a high school is much younger than the entire population of a city. So it's not random, nor it is representative. Or let's see another example. Suppose we have a classroom of 30 students that we have 15 male students and 15 female students in that class. If you want to take a sample that is representative of this population of students, for example, we take a sample of 6 students, then we should have 3 male students and 3 female students to be a good and representation of the population. A little statistics joke. Did you know statisticians would fall faster because they take a random sample of sheep and they don't have to count all of the sheep? How variation in sampling occurs. Suppose we have a population of different numbers, but we don't know much about this population. For example, we don't know the mu, the average of the population, or sigma, the standard deviation of the population. So we want to use sampling to estimate these parameters. For example, we want to take a sample of 5 numbers here and then compute the average of the sample to estimate mu. We could take these 5 numbers as our sample, and the average would be 31.6. And this is an estimation of mu. Or we could take these 5 numbers as our sample. The average of this sample would be 33. So 33 is our estimation of mu. Or we could have taken these 5 numbers as our sample. The average of this sample is 35.2. So this is another estimation. As you see here, the estimation or the sample varies here. This gives us an idea. We could actually define X capital bar as a random variable that represents these averages of these samples. We're going to call it sample means. Sample means takes these values, the average of different samples that we can take. How many samples but we can take? If n is capital N is the size of the sample, the population, and n, a small n, is the size of each sample, then the total number of possible samples that you can take from a population, you can actually use the counting rules to compute that. Since the order doesn't matter, the total number of samples possible would be the combination of capital N and N. Variation among sample means is measured by their standard deviation. A standard deviation of sample means is called a standard error. The mean and a standard deviation of sample means. So we learned that x bar is a random variable. It's called sample means. As a random variable, we can find the average or the mean of x bar. The average of x bar, which is also called the expected value of x bar. What is the average of x bar? Or the expected value of x bar? The mean of the sample means is the same as the mean of the underlying population distribution, mu. This means that the expected value of x bar, or the mean of x bar, is mu. And that is very interesting. So the expected value of x bar, or the mean of x bar, is equal to the mean of the population. What does it mean? This means that x bar means the random variable representing the average of a sample. So if we take all of the possible samples from a population, for example, the first sample, the average is x1 bar. The second sample, the average is x2 bar. Suppose we have m samples. So the last sample is xm bar. The average of these samples, meaning if we actually sum these up and divide them by the total number of samples, which is m, this is equal to mu. Very interesting. We can also find a standard deviation of x bar. The standard deviation of the sample means is related to the standard deviation of the underlying population distribution. The standard deviation of x bar or sample means is actually equal to sigma, the standard deviation of population, divided by a square root of n, which is n is the size of the sample. This is called a standard error. The standard deviation of the sample means is often referred to as the standard error. That's why we call it SE. So SE is the standard deviation of sample means x bar, which is called the standard error.